Hello, everybody. Okay, today we will talk about the more forces, the effect of electricity and magnetism. Okay, this whereby we look at how if we actually look at current and magnet, okay, as two individual guy, okay, what happened when I put them together? Okay, I look at the interaction between the magnet and a current, the interaction between them, what actually happens when I put them together side by side. In the previous few topics that we talked about, right, we actually look at magnet and current as like a linear progressions, whereby I actually have a single item and I generate a current, and that particular item, the current inside that item actually generate a few line. Okay, a magnetic effect. That's what we call the magnetic effect of current. But here in the past few topics, we only look at one item which possess current and indirectly create a magnetic field lines. Here in this next section of the video, we look at, like I mentioned, we look at two items having current and the other item having the magnetic effect. Okay, so it could be maybe a piece of wire with current and a piece of magnet. So what happens when I put them together, and what is the outcome of that particular interactions? Okay, now this is what this topic is about: the motor effect, the force due to magnetic field. Okay, now let's take a look. Now, on this section here, we look at one of the interesting effect where we have a current and a magnet in this case. You will find that when I have these two placed together at a certain orientation, a third item, a third person, or a third character will actually be induced. Okay, and that's what we call a force. Okay, when you have a current and a magnetic field lines, okay, at a certain orientation. Okay, for example, the current is flowing from A, B, C, D. Okay, it's flowing from down, in, and up. Okay, and the field lines, the magnetic strength or magnetic field lines you are looking at is north to south. Okay, north to south. Okay, so you'll find that the current, the current or the wires with the current inside will actually experience a force. Okay, and that force is because of the interaction between the field and the current, and that effect is what we call a motor effect. And the guy that actually simplify simplify the identifying of the direction of the force is Fleming. Okay, Fleming derived a single, I would say, a shortcut to identifying the force, which he named it the Fleming left-hand rule. Okay, it's whereby you look at your left hand rule, the fingers. Okay, each of the finger represent a single character. Your motion, which is a force. The feel, which is the second finger. Okay, the index finger, which is the feel. The feel here represent the magnetic field, and the middle finger here will represent the current. Okay, you'll find that there are three parties here, and here we are looking at the interaction between the magnetic field lines and the current. So these two will interact to produce the third party, which is what we call the force. Okay, and this is what we call the effects of the magnetic effects. Okay, the force induced. Okay, and it has to be a certain orientation. Here, the orientation we look at is actually right angle. They have to be at a certain orientation. Okay, now when we look at this as example, the example that you see on the screen now, you'll find that the current is flowing towards from B to C. Okay, so how do I use Fleming left-hand rule? Of course, I have to use left hand now. So how do I use the Fleming left-hand rule? Is force field current. So normally what I do is I would settle one, instead of like using the whole hand, I'll use finger by finger. Okay, so now take note, the field line that we mentioned here, this is what we call this field line, this index finger actually, to me, is like I will mimic it to be north and south. So to some people, they always say that the index fingertip always point towards the south. Okay, so current in middle finger, that current actually is the current direction. Okay, the force is the force direction. So how we do? So if you look at the picture here, okay, you'll find that the field is going upwards, north to south. Okay, if I use my left hand rule, you'll find that I always start off with my index finger, the field line. Okay, the field finger. Okay, so the magnetic field finger, I will always, let's say based on this picture, the field line is actually pointing upwards, north to south. So my index finger, remember the index finger whereby give me a minute first. Let me expand the screen first. Okay, so now let's take a look. So the field line is pointing north to south. So my index finger will point up. Okay, remember the tip of the finger actually point south. Okay, now my current is going from A, B, C. So if you look at the magnetic field line, the north-south direction here, my current is pointing inwards. Okay, so it's pointing inwards to the screen, inwards to the monitor screen. Okay, which is here. This is the current that we are referring to. This is the current. This is the magnetic field lines. So magnetic field line is upwards. Current is, which is my index finger, is inwards. So I point towards my computer screen. Okay, you can do it also. You can practice. Okay, so field line is upwards. Finger by finger, field line is upwards. Index finger, index finger, it points towards the screen. After that, what you do, you let go your thumb. Release your thumb. You'll find that your thumb will point to the right side, which means that this force will actually pushes the wire to the right. Okay, so example, this is the wire, the current is flowing inwards. Okay, field line is upwards, so my force will push the wire to the right this way. Okay, so this is what we mean by the magnetic effect of the current itself. Now, because of time constraint, I can't really go dwell on too much example on this, but the usage of your magnetic effect, the usage of Fleming left-hand rule, one of the I have to applaud to you to say that the understanding for that 2 or 3 minutes, if you understand how we use Fleming left-hand rule, is really good already. Okay, but one thing for those one thing for those who are still blurred or still confused about the Fleming left-hand rule, because of time constraint, I can't really go much into it. But if you have any questions, okay, remember to just rewind a few minutes to read through the left-hand rule again. If not, okay, please leave a comment or come and look for me during class, okay, to run through the usage of Fleming left-hand rule. Okay, there are various examples that we can use even in the workbook or even in the worksheets to run through the usage of Fleming left-hand rule. Because the usage of Fleming left-hand rule to identify the correct force direction, force induced, is utmost important. Okay, because in exam, you have to get that direction correct first. Okay, before you can actually explain that, you can actually score any marks. Okay, so please look for me or your teachers. Okay, for if you are still confused about the left-hand rule. Okay, but other than that, okay, other than using the left-hand rule, the other one that I'm concerned is the writing. Okay, when we explain left-hand rule, when we explain to teachers, we explain to your marker that force pushes the wire left or pushes wire right, or there is a structure, which means you have to write in a certain way, certain keywords have to be used so that the marker actually knows that the students actually understand left-hand rule, understands force induced, understand what is the effect of electricity and magnetic field lines. So what I've done is I have crafted out 3 keywords or 3 key phrases that students you can use. Okay, but to use this key to make sense of the keywords, to make the keywords useful, the same as before, like I mentioned before, the usage of left-hand rule to identifying the direction of the force induced is utmost important. If the direction is wrong, whatever keywords, key phrases you use will be automatically wrong. Okay, there won't be any error carrying forward. There won't be any benefit of the doubt, because the force induced is wrong means the usage of the Fleming left-hand rule is wrong already. Okay, so that's why I urge you, if you have problems looking at or using the left-hand rule, okay, please either read or rewatch the video at the front at the last few minutes ago, or actually come and look for me or your physics teacher to understand how the usage of Fleming left-hand rule. Okay, you can go back to your teachers. Most of the physics teachers, they are quite well versed in this. Okay, you can go back to them. Okay, to get your facts, to get your concepts straightened out, and that will be the easiest thing to do. Okay, so if you have done that, okay, then the explanation that you have, it will be quite straightforward to explain Fleming left-hand rule. So after you use left-hand rule, you know the direction already. Okay, so for example, in this question here, the blue line will represent the current, the red one will represent the field line. So I will use the field line. I will use my index finger first, north to south. Okay, pointing upwards. My south is here, so you always point south. My current direction, which is into the paper, into the screen, which is my index finger. After that, I let go my thumb. It will be pointing to the right. Okay, so my force will be there. Will be on the right side, pushing the wire to the right. So how do I explain to the marker that this is what's happening? Okay, so I craft out 3 sentences. So for students, you need to take note that you have to tell the marker that, you have to tell the marker, firstly, the condition of left-hand rule. Okay, do not have the habit of writing by left-hand rule. For example, because of Fleming left-hand rule, the force induced is right. Okay, because that statement is fairly useless, because by saying you are using left-hand rule, the marker will not know that do you really understand what is left-hand rule? Or is it just a phrase that is just copied? Okay, so don't just stick on to say by using left-hand rule, therefore the answer is so and so. So what I need you to do is, what I urge you to do is actually break down the words. Okay, for example, the first sentence I encourage you to write is you have to tell the marker that the current and the magnetic field lines is perpendicular to each other. Okay, because this is the underlying condition for Fleming left-hand rule. The field lines, okay, and the magnetic field line, and the magnetic current has to be perpendicular to each other. Okay, before you can use them. Okay, then after that, and because of their interactions, you find that the force induced, remember the use of word induce, induce means it's indirectly created. Okay, it's a secondary process. Okay, when the force is induced, and I need to know the direction, which is right, left, up, down, towards so and so, away from so and so. So I need to know direction. Okay, so this is the one that you need to be correct. Then after that, you have to tell the person. For example, if I say the force is to the right side, but right side, there's a lot of right side, meaning the right side can be, it can be this way, it can be this way, it can be this way, this way. All these are right side. I can go bottom right, also call right side also right. All these orientation are right side. I can even be like somewhere in, somewhere out. It could be right side also. So which orientation of right side do you need? Okay, because remember in Fleming left-hand rule, like I mentioned before, these three fingers or these three characters, they are oriented at a certain directions. For example, force, field, current, they have to be 90 degrees to each other. So which means when you talk about right side, when you talk about the force moving to the right side, okay, you have to make sure that if the force is going to the right side, it must be perpendicular to the other two characters. So that's why the third keyword that I urge you to write is actually to tell the marker that the direction of the force induced is perpendicularly to the current and to the field lines. So this is what I mean by the key three phrases to unwrap what we mean by Fleming left-hand rules. Okay, so when you talk about you understand Fleming left-hand rule, meaning that you actually need to write or you need to know these three ABC to understand what is the fact or what do you mean by Fleming left-hand rule. Okay, other than to use it correctly, yes, to know the force induced is to the right or left or up, yes, but you also need to write to the marker. Tell the marker that you actually understand every bit of the Fleming left-hand rule. Okay, now same thing, if you reverse the directions, okay, you can try out in the picture before that, okay, the slides before that, okay, later on, okay, if you reverse the current direction, let's say DCBA, you should be, this one means the field line is still up, so the magnetic field is still upwards, north and south. Okay, so this is the where the field line is still north to south. So the field line is same, up to south, north to south, upwards. Okay, but now the current is reversed. So you'll find that if you use Fleming left-hand rule, the direction will be pointing to the left. Okay, please go ahead and try. Okay, please go ahead and try. Okay, pause the video if you need to. Okay, to go and try out these things, this Fleming left-hand rule, because it is utmost important that you can get the direction correct every time. Okay, so remember to pause the video to try it out. Okay, now same thing for the third one. Okay, same thing. You can actually follow stick the current direction to be the same, A, B, C, D. But what you do now is you reverse the magnetic field. Meaning now my magnetic field line is actually this way. North is here, south is bottom. Okay, so if you reverse the thing, you'll find that the wire will now swing to the left. Same thing, if you need to, please pause the video and go back and use these conditions and try it out to make sure that you actually get the force induced to be on the left side, to get your thumb to be pointing on the left. Okay, it's utmost important. Now, same thing. Okay, there's another way of explaining the thing, explaining the Fleming left-hand rule, but it's a bit tedious. So that's why that's the wonder of using Fleming left-hand rule. Fleming left-hand rule actually is more or less, it looks like, it behaves like a shortcut for us to actually identify the force induced. But there's another way of explaining, which is by Maxwell. Because Maxwell uses field lines. He look at the interaction of field lines. Okay, to identifying interaction of field lines, to identify the direction of the motions. So this is what Maxwell theorized. Okay, is that if you have the wire and the field line, okay, so you have a wire and a magnet itself. So this is the wire with its own magnetic field lines. This is the magnet okay, with its own field line. So what you're going to do is, because the wire is inside the magnet, okay, so the wire is inside or in between the magnet. So the two field lines, one field line by the current, one field line by the magnet, they will actually interact. So what you do now is, I will look at the interaction. So if you superimpose these two pictures together, you'll find that if, as I do this, if I superimpose the wire here, okay, let me try this. Okay, now let's take a look at this. Okay, so let's say if I use a short one, this is a field line by the cable. Now, let's say I use another color. Okay, then the green one will represent the field line by the magnet. Okay, so you'll find that here what we have is you have the interaction of these two field lines. What happened here is this. Give me a minute, let me change the color. Okay, so now what you have is interaction of the two field line. You find that on the left side here, you'll find that the red color and the green color, the red color and the green color, the red color and the green color, let's say on the left side, okay, this side, this left side, you find that these two, the two arrows, the green and the red, are actually in the same direction. So that's why the two field lines, because they are in the same direction, they will reinforce each other. So this field line, the left side one, will actually be stronger than before. Okay, because they are in the same direction, they will reinforce each other. But if you look at the left side now, if you look at the left side, you'll find that the green and the red, they are in opposite direction. Take a look, the green and the red, they are in opposite direction, which means they will actually, they will have some cancelling effect because they are in opposite direction. They will cancel out each other to a certain degree, such that this side here will be weaker. So now when we superimpose, we overlap these two magnetic field lines together, you will find that the interaction of this field line will cause the left side here, the combined field lines, the eventual field line, the resultant field lines to be stronger. And the resultant field line on the right side here will be weaker. So you will have one side be strong and one side is weak. And what is the outcome for this? And you will have the status, you will have a final few lines which look like this. So because remember, the right side is strong and the left side is strong. Okay, so what happens is when you do this, you'll find that you will have an area which is of strong and a weak. And like Mother Nature or like by law of nature, you'll find that the strong will always eat the weak. The law of nature, the strong was the fittest of the strongest. And because of that, the strong will try to push the weak in the direction. So the strong will always try to take over the weak. So that direction is always from the strong to the weak. So that's why the wire here will be pushed to the right. Okay, and this is how I get the wire to be pushed right. Okay, yeah, of course you can use, if you look at it, you can actually use Fleming left-hand rule to derive the answer quickly. For example, in this case, the field line is the force field current. So I will start with the field, the index finger. You will point upwards, Y is always point north and south. Current is X, means it's away from the screen, it's coming towards you. So okay, so you have a Fleming left-hand rule. Sorry, X is towards, away from you. So X is away from you. Field is up, current is away from you. You let go of your thumb, you'll find that the force induced, the thumb will point to the right, which has the same answer as Maxwell. Okay, but of course, if you look at the degree of complexity, in Fleming left-hand rule, is much easier to derive the outcome easily. But it works like some sort of a shortcut for students to use left-hand rule to find the force induced. That's why Fleming left-hand rule is actually quite useful to find the force induced. But of course, likewise, you can also use Maxwell to identify the force induced also. Maxwell interaction of the field lines does work out the same answer also. Okay, so here in the summary, we look at the idea of the interactions between current and magnetic field lines. Okay, and to give rise to a third party called force induced. And of course, the force induced that we are looking here, it arises because of very few lines and current at a certain orientation, and that orientation is perpendicular. So here we look at one thing. Okay, you need to identify the correct force induced. I need to know the force induced direction. That's the first cut that you need to know. And to do that, you need to use a left-hand rule clearly. And of course, once you use left-hand rule clearly, you can get the answer of left-hand rule. The next thing that you need to actually know is actually to present your answer clearly to the user. And to do that, you must remember the keywords. Okay, to use the correct keywords to illustrate the meaning that the students will need. And that's one of the things that you actually need to know what is your force directions, your force induced directions, using the left-hand rule. Okay, with this, okay, it wraps up at the end of the left-hand rule. If you have any problems regarding left-hand rule, okay, remember, same thing I urge you, okay, go back to look at this video again. Look at the workbook, look at your textbook again if you need to. If not, go back to your physics teacher again. Okay, look for your physics teacher to get these things sorted out straight away, because left-hand rule is one of the important topics or one of the hot topics in the exam. Okay, and it's not difficult to understand. It may sound complicated, but there is a structure towards it, and it's actually quite easy one. Okay, so look for your teachers. Okay, look for your teachers. Okay, I'll re-watch the video. If need to, if it's small problems, you can actually leave your question in the comments bar below, and I'll try to get back to you ASAP. Okay, if not, okay, remember to subscribe to the video for the latest update for the last topic, okay, the last video, okay, for this year. Okay, if not, okay, thank you very much, everybody. Have a nice day. Lunchtime soon. See you.